All right, so hello everyone. My name is Fabian from DTH of Zurich. I'll just give you a very brief overview over my master thesis and what I did before the break. So, as Davide Rossi talked about in the morning, we focus on very low-level, low-power chips. And in these processors, we have a lot of caches, very small memories. That can be cumbersome to make work at very low voltages or use very low energy. So if we take a quick look at a regular SRAM that you find can be generated for ASICs, you'll find that if you make the SRAM very small, you start to have a lot of overhead of the surrounding circuitry. So if you look at the SRAM, there's actually the area that stores the bits is very small. It's just these small rectangles. And everything that's around is sense amplifiers and the power ring and other overhead. Especially the power rings require a lot of spare room around the SRAM when you want to place it alongside with standard cells. So if you make SRAMs very small, you start to waste energy because you have sense amplifiers which require a lot of energy to operate. And it's also very, well, it doesn't like if you lower the supply voltage as we've seen this morning. And to a certain extent, it also wastes area. So the approach to mitigate this for the caches in use and to regain some energy efficiency is to build the memories from standard cells. So what you do is you describe your memory in HDL source code, you synthesize it into a cell netlist, and then you place and route it with your regular placement and routing process. And you end up with basically a sea of gates that implements your memory. And as Davide said, this is used in the pulp chips for the instruction caches. So if we look at Fulmine, which was one of the pulp chips that was taped out in 65 nanometers, in the upper area where the cluster sits, you can actually see the instruction cache SCM here highlighted in red, which basically flows through the gates. Yes, please.
Cells. I assume the synthesizer compiles it into flip-flops.
Yes, yeah, it does.
Okay.
It does. All right.
It is let's base the usual solution we use. Yes.
Yeah, if you go a step further, if you start to pick the cells yourself, you'll go for more area efficient and NA efficient cells. So if you go one step beyond just behavioral modeling, but picking the cells yourself, you would go for latches, as is done in pulp as well.
So if you go for latch-based memories, then how do you test these memories? It's logic, so you need to start inserting scan chains, and latches kind of mess up your scan chain.
So we have already answered this question. We are making beasts around the memory, and with special finite state machines to test all the memories and all the ports and so on.
All right, so one approach to make these things more efficient, to make the SCMs, the standard cell-based memories more efficient, is to manually place the individual cells. So instead of just having the placement tool put them wherever it wants in the design, you constrain it and basically take its hand and guide it. So there's been recent work investigating this, doing very controlled placement. It has been shown to deliver a very significant energy savings in 28 nanometers. So as I said, what you do is you manually pick the cells, you generate the netlist by hand, and then you place the cells manually during placement and route. So basically, you change the sea of gates that you had to a more structured and more regular pattern, which reduces your wire lengths and gives you energy savings. So this is where my master thesis came in. I did my master thesis at the Integrated Systems Laboratory, where the pulp chips are partially being developed. And my task was to basically build a tool that produces fully routed and ready-to-use hard macros for these SCMs. So rather than placing them during the place and route process, you would have this tool that generates the macro, which has all the standard cells already pre-placed and pre-routed. So the routing of the finished design becomes much more easy. And then to take things a step further, I improved on this control placement by merging the standard cells and creating custom cells that leverage a few reusing opportunities that you have and does manual routing. And the key goal is here to remain compatible with the standard cell grid, so you can just place the macro in your design. So Potstill is basically just a collection of Python and Bash scripts, and it relies on a separate C program and C libraries that were all developed as part of my thesis to do its work. So what it does is it takes input from the user. Currently, it's just a number of words and the number of bits you want to have in your memory. And it produces, for one, the layout, which you want to include in the final design. It produces lef and lib files, which allow you to integrate the memory properly into the standard design flow. So you have timing, energy characteristics, and you can basically place it as a very big standard cell. And it provides you with a simulation model. So for one, a VHDL model, so you have a behavioral model, and also SPICE netlists to do verification later on. And to do this, you basically have 10 building blocks. There we go. So basically, to build the memory, my generator requires 10 basic building blocks that you need to lay out manually once per technology. It's basically just a few logic gates, the core latch, and a few auxiliary tools. So with this done, you need to build an energy and timing database, and this allows you eventually to just ask the program for a memory of a specific size, and it will give you a fully routed macro without relying on any proprietary software. So it's all fully open source once the, once the initial effort has been done. So it does this by basically dividing the area into segments, address decoders, where the bits go, things like that. It plans where the individual cells should go. It instantiates the cell, adds additional routes, and there you have your finally fully routed memory. So the key benefit here is that it's all pre-routed and it's pre-characterized. So it plays well with standard cells. So the macro fits exactly into the standard cell grid, and it can be abutted to standard cells horizontally as well as vertically. So on the left, you see, well, you barely see the standard cells of surrounding design. On the right, you see the memory macro. So it plays well with this, with the power grid of the cells. You can just place it there. And if you look more closely at the layout, you can actually see that it's a perfect match. So all the wells just flow into the memory. So it's a natural part of the design. So when I compared it to a regular SCM approach, just instantiating the cells and then letting them being placed and routed, you get up to a 13% area reduction just by reusing parts of the flip-flop or latch cells. But even more, you get a lot of reduction in power consumption because everything is pre-placed and pre-routed. You know exactly how long the wires are. You can optimize transistor sizes, reduce leakage significantly, and by reducing the gate capacitance of the individual cells, you can reduce the energy consumption significantly. There's some future work that's going to happen, so it will be interesting to port the generator to a different technology. Currently, it's a 65 nanometer process node. It'll be probably ported to 40 nanometers to experiment with it. It'll be soon tested in silicon in probably a student design. And, well, there's lots of room for improvement. But hey, it should be made to scale better as the memory becomes larger, and there should be less technology-specific things in the generator, but there's lots of options. So with that, I want to close. Thank you very much for your attention. The code is available on GitHub alongside with all the other dependent projects. Cheers.
Thank you.